Right now, as you read this, you assume something so basic about your life that you've probably never once questioned it. You assume that right now means the same thing for everyone, everywhere, that somewhere across the galaxy at this exact instant, there's a now happening too. Here's the uncomfortable truth. There is no universal now. Not somewhere else in the galaxy, not even for the person sitting next to you. Time, the thing you have never once doubted, does not work the way you think it does. And the story of how we found this out involves a patent clerk, a mathematician who got mocked for taking his student's idea seriously, 2 flying atomic clocks, and a mathematical loophole that technically allows time travel. Let's start with what everyone believed before this got complicated. For over 200 years, the accepted picture of time came from Isaac Newton. In Newton's universe, time was a single, universal clock ticking at exactly the same rate everywhere, for everyone, always, past, present, and future were fixed. Now on Earth was the same now on the other side of the universe. This wasn't just intuitive. It was built into the foundation of physics for 2 centuries. And then in 1905, a 26-year-old patent clerk in Switzerland who couldn't get a university teaching position published a paper that quietly destroyed it. His name was Albert Einstein. Here's the thing almost nobody tells you about this discovery. Einstein didn't invent the core math out of nowhere. A Dutch physicist named Hendrik Lorentz had already worked out the strange equations describing how measurements of space and time would need to shift for light speed to stay constant years earlier, while trying to explain a completely different experimental puzzle. Lorentz treated it as a mathematical trick, a strange bookkeeping device to make the equations work. He didn't believe time itself was actually changing. Einstein looked at the exact same equations and asked a completely different question. What if this isn't a trick? What if this is just what reality does? And that reframing changed everything. Einstein started with one simple assumption. The speed of light is the same for every observer, no matter how fast they're moving. That sounds harmless. It is not harmless. Because if the speed of light has to stay constant, something else has to give, and the thing that gives is time itself. Here's the twist that trips almost everyone up. Imagine you're on a train moving near the speed of light, and I'm standing still on the platform watching you go by. From my perspective, your clock runs slower than mine. Here's the part that should genuinely break your brain. From your perspective on the train, it's my clock that's running slower. Both of us are correct simultaneously. There is no referee, no universal clock keeping score. Whose time is really slower depends entirely on who's asking. This idea has a name, the relativity of simultaneity, and it means 2 events that happen at the same time for you might happen at completely different times for someone moving relative to you, not because of some illusion or delay in how the information reaches you, because at the same time genuinely isn't a fixed universal fact about the universe. It depends on your reference frame. Now, here's where the story gets a name almost nobody remembers correctly. In 1908, a mathematician named Hermann Minkowski, who had actually taught Einstein years earlier at university, and reportedly found him to be a rather unremarkable lazy student, gave a lecture reframing Einstein's work in a way that changed physics forever. Minkowski proposed that space and time aren't separate things at all. They're a single, unified fabric. He called it spacetime. In a now famous line, Minkowski declared that space by itself and time by itself were doomed to fade into mere shadows, and only a union of the two would preserve an independent reality. Einstein was initially skeptical of his old professor's reframing. He reportedly considered it overly mathematical, unnecessary complexity dressed up as profundity. He would later completely reverse that opinion because 10 years after that lecture, when Einstein extended his ideas into general relativity to include gravity itself, Minkowski's space-time framework turned out to be exactly the tool he needed. Without it, Einstein's greatest work might not have been possible at all. So now we have 2 people, one who saw the equations and dismissed the implications, and one who reframed them into the exact tool needed for the next breakthrough. And history mostly just remembers the third guy. But this is where things stop being theoretical. Because gravity doesn't just bend space, it bends time too. The stronger the gravity, the slower time moves relative to somewhere with weaker gravity. This isn't a metaphor. It's measurable, verified, and something you rely on every single day without realizing it. The GPS satellites orbiting Earth right now experience weaker gravity than we do on the surface, which speeds their clocks up slightly. They're also moving fast enough that special relativity slows their clocks down slightly in the opposite direction. Engineers have to correct for both effects precisely every single day. If they didn't, GPS location errors would accumulate by about 6 miles every single day. Your phone's map app works because of relativistic time correction happening in orbit above your head right now. And here's the experiment that proved humans could measure this directly, using nothing more exotic than commercial airline flights. In 1971, 2 physicists, Joseph Hafele and Richard Keating, loaded extremely precise atomic atomic clocks onto commercial airplanes and flew them around the world, once eastward, once westward, while identical reference clocks stayed on the ground. When the traveling clocks landed, they had ticked a different amount of time than the stationary ones, a few hundred billionths of a second, but exactly the amount predicted by relativity in exactly the direction predicted. Time doesn't just theoretically dilate. It dilated measurably in cargo holds on regularly scheduled commercial flights, and scientists wrote down the receipts. And if you want proof falling from the sky, literally consider muons. These are subatomic particles created when cosmic rays slam into our atmosphere and they decay incredibly fast. So fast that without time dilation, almost none of them should survive long enough to reach the ground. And yet we detect them at sea level constantly, because from our perspective, moving near the speed of light slows their internal clocks down, letting them live just long enough to make the trip. You are, right now, walking around bathed in experimental proof of relativistic time dilation, and you've probably never thought about it once. Now, here's where the story takes its strangest possible turn, because if gravity can slow time down, what happens near something with truly extreme gravity? Near a black hole's event horizon, time dilation becomes so extreme that from an outside observer's perspective, someone falling in appears to freeze, fading redder and dimmer, never quite crossing the edge. From their own perspective, they cross it instantly, feeling nothing unusual happen at all. Two completely different, equally valid timelines for the exact same event. This isn't a paradox, it's just what spacetime actually does when gravity gets extreme enough. And this brings us to the strangest name in this entire story. In 1949, a mathematician and logician named Kurt Gödel, one of Einstein's closest friends and colleagues at Princeton, gave Einstein an unusual birthday present, a mathematical solution to Einstein's own equations describing a rotating universe. And buried inside that solution was something staggering. In a rotating universe, the equations technically allow for closed loops through space-time paths that would let an object return to its own past. Time travel, not science fiction. A rigorous solution to Einstein's own field equations, mathematically valid. Einstein reportedly found this deeply unsettling. He acknowledged Gödel's solution was mathematically sound while spending real effort trying to argue why it probably didn't describe our actual universe, since as far as we can tell, our universe doesn't rotate the way Gödel's model required. But the fact remains, somewhere inside the same equations that gave us GPS corrections and gravitational time dilation, there is a mathematically valid loophole for traveling backward through time. We've simply never found a physical situation where it applies. So let's step back and ask the question we started with. What is time, actually? It's not a universal clock ticking the same everywhere. It's not separate from space. It bends under gravity. It slows down near mass and speeds up far from it. It runs differently depending on how fast you're moving, and there is no cosmic referee to declare whose clock is correct. The now you're experiencing this exact second isn't shared by the entire universe. It's shared at best with whatever is nearby and moving roughly the same speed you are. Everything beyond that is a negotiation governed by geometry that nobody bothered to tell you about, because on a human scale, moving at ordinary human speeds, the differences are so microscopically small that you'd never notice them without an atomic clock and an airplane. But they're there. They were always there, even before Einstein looked at Lorentz's equations and decided to take them literally, even before Minkowski gave his old unremarkable student's work a name that would outlive them both, even before Gödel handed his best friend a birthday present containing a mathematically valid escape hatch out of the present moment. Time was always doing this. We just spent 200 years assuming it wasn't. If questions like this, the ones where the answer rewrites something you never thought to question in the first place, are exactly what fascinates you, this channel exists for precisely this kind of thing. Subscribe to the Zodiac Archive, because right now, somewhere, for someone, it's already a different time than you think.